Hello, this is Rohan, and this is my EE782 assignment 2. My roll number is 20D170033. So I'll just go over the code. These are importing the libraries. This is to check if there is a GPU. This is to download the dataset. This particular file is to find out how many people are having more than one image as per this question 2. Then we just print it. Then this code is to split it into test train and validation. This is the Siamese network dataset class which will extend dataset. We will just check whether in order to distribute it uniformly we randomly sample names, and then with probability 0.5 we assign them same class or different class. This will even return the label, and we use 1 and -1 for same and different. This is some code to visualize this. So for example here these two are the same person, so it is 1, and on the other hand like, these two people are different, so the fourth image has -1 label, so it's working fine. Then we use ResNet 50 as our base model, which is trained on ImageNet, and then these are now for the training we use a size of 224 cos 224, which is the input to the ResNet 50. Now we define our Siamese network, which will use the base model as ResNet 50, and then we freeze their weight so that we can perform transfer learning. Then we have a fully connected layer. Then this is the training loop. This part does the calculates the training loss and does backprop, and this part does the validation accuracy calculation. There is a threshold value which you have chosen right now as 0.8. If this value is more than 0.8, if the cosine similarity is more than 0.8, that means they are the same image, else they are different images. So this is some code to visualize the loss. So we perform training without regularization and image augmentation first. After performing this, we get this some sort of result where these two images are similar, so we are getting a similarity score of 0.95, whereas these two images are different, we are getting a point score of -0.11. So it is working as intended. So after performing testing with the test images, we get 68% accuracy. Now we add image augmentation, where randomly we apply horizontal flip or rotation or jitter or Gaussian blur with probability of 0.2. After performing this, we see that the accuracy has increased to 72% from 68%. Then we add regularization also. We add dropout with probability 0.15, and we also add L2 regularization with 0.001. So we have added dropout after each layer, and also here added the weight decay coefficient for L2 regularization. Now we see that the accuracy has become 77.88%. Now we apply learning rate schedulers. So we take since it has improved, we take both image augmentation and regularization from now on. So first we use step LR, which uses of step size of 15 and gamma 0.5, which means it will halve the learning rate every 10 epochs. So after doing this, here epoch is getting halved after 10. So we get accuracy of 72%, which is lesser than the 77% earlier. Then we also try using polynomial LR with total iterations of 120 and power 1, so that it will go from starting learning rate to half of it over the 75 epochs. So here also we see that we get 74%. We see that both of these are learning rate schedulers are working fine, but they're still not able to compete with the value of lesser learning rate which is used in the previous sum. So we will not use learning rate scheduling from now on. Now we used AdaGrad for the above part. Now we will try using Adam optimizer to see if there is any improvement. We used Adam optimizer, and we have changed the learning rate and decay coefficient accordingly, and we ended up getting accuracy of 76%, which is very similar to what we got with AdaGrad also. So we go ahead with AdaGrad because that was 77%. Now we perform testing on test split. We create a new testing split of size 500. Earlier it was 100. We use the best weights so far. And then we can see here for this image its similarity is 0.99, for this it is minus 0.38, so it seems to be working intentionally as it is supposed to work. So now we see that we have got an accuracy of 80.76 with the new test data, which is a very good score for given just 75 epochs of training. Now we test it on me and my friend's images. So this is a function to get my photo, his photo and another person's photo, and this particular thing generates the photo and performs inference using the model we used earlier. So this is my photo, this is my friend's photo. We are getting a similarity score of 0.78, and this is another friend, and three of us. When you compare these two, we get 0.81, and when we compare our faces, we get 0.91. When we compare my own face, we get 0.98, and when we compare these faces, we get 0.988 again, and here these two faces 0.996. We see that it is performing, it is able to capture similarities and disparities, but the threshold value is different. So we have to use a threshold of 0.9 or something in this example instead of 0.8. This may be because the background conditions and lighting in all of these images are the same because they are taken in the same place. So it seems to be working well for our images as well. Now moving to part B using GAN. So I use this reference from the CGAN, which uses CGAN architecture, and this is mentioned in official PyTorch tutorial. So I have changed the hyperparameters according to this application, and I've set the root directory as LFW for the labeled faces in the wild dataset. This is a thing to visualize images. So we use the image folder dataset, and we set the batch size to be 64 for now. So these are some sample real images which we use. So this is the class for the generator. So this is the architecture for the generator. We use relu as our activation functions, and then we perform transpose convolutions of the z vector and finally we use a tanh activation at the end. Similarly, in discriminator we use leaky relu and batch norm for everything. Even here we use batch norm, and we perform convolutions and then finally pass it through sigmoid. We use our loss criteria as binary cross entropy loss, and then for visualization we just create a noise vector of size 64 just to visualize 64 new faces. So, and this is the two optimizers which are using for each of discriminator and generator. This is the training loop. So here first these are the things to capture the average values, and then we first visualize the fake images generated in the flow for validation. Then we zero out gradients, then we perform the steps here and we backpropagate. Similarly, we use the discriminator to find that, then generator to use the noise and generate fake images, and then we calculate the total error, and then we zero out gradients and then perform backpropagation for the generator. Here we performed for the discriminator. We perform this for 10 epochs, and then after each epoch we visualize the generated images. So after 9 epochs we see that it is doing a very good job of generating faces, and after 10 epochs we see that it has generated lots of faces which look like humans. We store the weights and then we compare it with the real images. These are the real images and these are the generated images. They look very humanoid and they are different. So our GAN is working fine. Now to modify it to become a conditional GAN. So we will pick only 5 people for now. So if our GAN is able to generate image of these 5 people being trained on these 5 images, it means we'll be able to scale it for every other. Because of lack of computational resources, I am using a smaller data set of just 5. So I'm making a new folder conditional and I'm moving these people's photographs into this. Then as shown in the video in the PS which is provided here, the changes were done to the original code which I have done. So I have added one more dimension to hold the label. Similarly, I'm creating an embedding layer which generates the embeddings, and then I concatenate these embeddings with the input. Similarly, even in the generator, we add one more embedding size here, and then we reshape the embeddings and then concatenate embeddings within input. This is to visualize, and also we modify the dataset over the image folder in order to make sure that even the label is returned along with the image. So this part does that. We apply transformations and resizing, etc. And so for this, one example of the batch. So this is a person, and then it's labeled 0. This is the same person labeled 2, labeled. So there are 5 people. So it labels from 0 all the way till 4. So, and then this is the mapping corresponding to this. So Tim Robbins is 0, Vince Carter is 1, and so on. So now we declare the classes and the criteria. This is the optimizers. This is and we also generate a fixed label, means 64 random labels just to make sure that they are for visualization. So 1, 4, 3, 0. So the fourth person is supposed to be Tim Robbins. So let us see. So this is the training loop. It just modifies to incorporate the labels as well here and then wherever the models are performing inference before the training steps. So after that, after one epoch, 2 epochs, 3 epochs, and 4 epochs, you can see it is able to generate spaces of those people. So now the fourth image is of Tim Robbins. This kind of looks like Tim Robbins, but it is a new image. So it is generated using. So we can see that the fourth image is again Tim Robbins. So this our conditional GAN is able to generate other images of the person. We store the weights. Now we will use Siamese network to identify best label for a given input image. So this function basically takes the person's name and gets a random image of this person. This is to visualize the 64 cross 64 version, which we will use to compare with the CGAN's output. This function, what it does is it goes over all the people and it takes an image of this person and the original image and calculates the similarity score with respect to the Siamese model, and then if this value is more than the maximum similarity, it assigns the best label to the person. So for now we are taking an example of Tim Robbins. So this is Tim Robbins image. Now we predict the label using get the best label, and then we see that it is predicting it to be 0, which is as expected. Tim Robbins is 0, means our Siamese network is working fine. Now we feed this predicted label to our CGAN to see if an image is generated of Tim Robbins itself by the conditional GAN. So this was the input image and the output image is different, hence, and it looks like Tim Robbins itself. Hence the conditional GAN is able to generate images of the person, and it's not just copying it, it is able to generate a different image of the same person because it has been trained on that. Thank you.